Okay, let's continue. Resume the class. Yeah. Let's resume the class. Okay, we are talking about the characteristic of inverse tie overcurrent relay. Okay, so as is shown here, is an inverse. So the vertical is tie and the horizontal is current. So it's inverse higher current, less time. So it's inverse. But to searching it's not continuous forever. It has an exponential curve. No, it's not. It's searching maximum current. We want to open the breaker in low tide, in zero tide. So when the current is reach the maximum, then we want to open it right away. That means it's the same as the instantaneous, not an inverse. Okay, others is a inverse curve. So the inverse tie overcurrent relay, responds instantaneously to the maximum setting or maximum current, but it will respond slower when the value is above the pickup. Okay, the less current, it responds even slower. Okay, the pickup. So in the pickup, pickup is supposed to be the maximum current it will operate, but it will take long time to operate. This exponential curve will meet at a certain value of the time. Okay. So how we decide the pickup current and all this will in your project you'll go through it. So after the project you will know how to do the design. And overcurrent, how you consider overcurrent, what margin you are going to give, all this will be included in the project. And also I will tell you the solution, at least one solution in the lecture. Okay, so other consideration you can try out your depends on your TA's instruction. Okay, but you always learn it first from the lecture. Okay, the inverse time characteristic provide the backup. As I say, you can wait. Okay, yeah, you can wait because of if the current is small, it's not you have to be responsible for it. Just like here. Okay, just let me give a very simple. I have a low here. I may have a low here. Okay, and I have a source here. Okay, I have a source here. So we put a breaker here, and we put a breaker here. So if there's a fault along this line, then this breaker, say with breaker 1, this is breaker 2. Breaker 1 will operate first. We'll open it up. Now, breaker 1 will see the current as just to make the argument simpler. Assume the line is the impedance is the same. Of course, it don't have to be the same. If it's same, so the fault here will be say IF. Now this will see IF and breaker 1 and breaker 2 both will see IF. Now how you distinguish which one is primary? Okay, so then it will depends on your setting. Depends on your setting. So even both are IF. Okay, if this is setting for 1, breaker 1, this is setting for breaker 2. So both will see IF, that much current. Breaker 1 will see IF, breaker 2 will see IF. But then breaker 1 will operate first because this is time, because it operates at T1. T1, it will operate first. Breaker 2 will operate at T2, is later. But if breaker 1 is operate properly, then the fault is disappear. So the breaker 2 will not need to operate. Okay, so we are going to do the design and all the detail of this. Again, this is simple. It's very simple. Okay, power is very simple. But if we are not careful, we don't do it correctly, the consequence is so huge. The cost is so huge. It costs the damage the equipment is one thing. Interrupt the operation is a huge cost. Now, the infinitive cost is a human life. Okay, if the protection is not properly protected, it may kill someone. Okay, so the design, everything very logically, very simple. But the consequence is huge, dangerous. Okay, responsibility is huge as a professional engineer. Okay, so, and you have after you learn this course, you have all the knowledge, all the capability. The only thing is missing is whether you do it carefully or not. That is something I cannot teach. Okay, I can provide you the exercise to make sure you are careful, so you are not ignore some of the important factor. But the bottom line is still you. Okay, it's still you. It's nothing to do with what I'm saying. It's you to careful, adjust it, make sure it tests it properly, make sure it commissioning it correctly, cover all the possibility. Okay, that's why sometimes it's 2 per person. Is you can talk, but 1 person sometimes you may miss something and you don't know, because it's very difficult to find your own mistake, because you have some idea, then it's difficult to say that idea has some drawback, and it's very difficult. Okay, but if you insist to have 1 person, then ask the TA to consider. I don't think it's a major problem. Okay, that's why this become a backup. Now, if you say if a fault here, then this will see a huge breaker 2 will see a huge fault. It's twice of the fault. If the fault is here, you will see twice. Twice means is here. This is 2IF. When 2IF, it will operate in T3 much sooner than T2. So it can distinguish. If it's not if not the circuit breaker's prime responsibility, it will wait until breaker 1 cannot operate, then it operates. But then if it falls into its own responsibility, that means the fault is twice as high, then it will operate faster. And this has been tested for almost 100 years. So it's nothing new, nothing difficult to understand, nothing new or difficult to learn, no. But it still have a loss of accidents and cause a loss of damage in the industry because the engineers are not careful enough, not think deep enough. It's not the university problem. It's a person. He may skip something and try to find a shortcut and all this. Okay, so careful. Since you take the second course in the power, I assume, I may be wrong, I assume most likely you will be working in power. Okay, power is very simple. You enjoy your career. Believe me, you pick a good career because it does not change that fast. But the consequence is very huge. Once you're employed and you do the good job, you enjoy life. I'm telling you, you don't need to worry about 2 years down the road and all the things are changed and you have to learn again, and then you cannot spend time with your kids and all this. It's not. You have a beautiful life, but make sure whatever you do, you have a huge consequence. Huge consequence. You don't want anyone killed because of your design.
Excuse me, can I just ask a question about the?
Yes.
So in this scenario, would the second breaker have like a higher capacity than the first breaker?
Correct. But the relay does not see whether high capability. The relay, the CT is still 5M.
Right.
Okay. You just change the turns ratio. We are talking about in the control. The control will see the same thing.
Right.
5M.
Okay.
5M. Whether it's 2IF will be equal to 5M to circuit breaker 2 for this example. 5M for breaker 1 is 1IF, something like that.
Okay.
So I put them together just to make a relative terms, but actually it should have the two curve. Okay, yes, two curves, two separate curves to tell you. I put them together so you are easy to compare.
Right. Okay, thanks.
Okay. Okay, very good. Good question. Actually, I like your question because I put it in that way. It seems I do not distinguish IF1 or IF1IF or 2IF. Okay, so I like the question. Believe me, I like the question very much. Okay, and other people in the class also please ask me question and you pay for it. Okay. Okay, the challenge is to ensure the minimum pickup such that is low enough to pick up all the fault, all the likely fault. Okay, so it will be low, but again, contradict now. It is high enough not to trip the normal low. Okay, you want to isolate the fault as quickly as possible, but you don't want to isolate a large area. Okay, you don't want the large area. You want to minimum the area, so that large and small contradict each other. Okay, low and high contradict each other. Okay, put it this way, don't complain about contradiction. Don't. If it's only one solution, okay, and your boss will not hire you, just buy a program. Okay, I'm happy because of the huge consequences. I'm happy because the conditions are contradict each other. I'm happy. Otherwise, I don't have consulting work to do. Because consulting work is ask your opinion and pay you good money. If there's only one way that is the best solution, written down in the or even programming and AI will replace it, then then we may have to get the free money from the government. Okay, maybe sooner or later that is the world. Everyone get free money from the government. Okay, the machine do everything, but not yet, not yet, not yet. You still have to make your living. So you don't complain about this contradiction. The contradiction is the reason we are higher. Okay, because of the contradiction. Okay, and because there's no unique answer. You are happy with no unique answer, because you are the person can do it. Not everybody in the street can do it. But if there's one solution, a program, and everyone just hit the button, can get the solution, then everyone can hit the button and get the solution. Then we have no job. Okay. So we are happy with challenger. We are happy with contradiction. We are happy. Okay. The outage filter return to the surface. Okay. When you clear the fault, you close the breaker, it may have a high inrush current to the motor. If every one or two motor which we turn on and turn off, then it's easy to deal with in the feeder. But when it's outage, the whole area back out, and once the circuit breaker put back the breaker, it may trip again, because all the motor, particularly in the industrial area, okay, all the motor will require a high current, okay, and the transformer take a lot of current, okay, and the transformer can take to 8 times to 10 times of the normal current or rated current. Okay, do you know why? Do you know why the transformer will take the current 10 to 8 to 10 times more than the normal current in the inrush, and the motor maybe take 6 times? Do you know why? Anyone can answer me? No, you learn the machine. You learn the machine in the 637. That is a prerequisite. I think prerequisite of your last course prerequisite. You learn it.
Okay. Those machines and devices have a higher starting current than the constant current, right?
Yeah. Why? Why the inrush current to the transformer is high? Why the inrush current to the motor is high? Why? My friend, I'm scared now. If 2-3 months down the road, you qualify as an engineer to make a living. If you cannot answer this question, then there's a problem. No matter how good you do, the short circuit test and all this, is people ask you this question in the job interview, and you cannot answer. And how many times you have to find the parameter of the transformer in a career? Less than 0.1%. 1,000 people may not have one person need to do that job. So all this kind of, I got an A+ on this course because I can do the calculation of the short circuit, open circuit test and all this. I got an A+. I did. Well, I cannot pass the interview. I cannot get a job. What's good for that? What's good for for that kind of things. I'm not saying it's not good. I just ask what's good. Okay, don't show me. Okay, don't show me. Do you know how the induction motor work? How the induction motor running? Why it turn? The synchronous motor, synchronous generator, how it turns? Well, I just know the equivalent circuit. I can do the calculation. No one asked you to do the calculation. No. I'm telling you, 1,000 engineer graduate is maybe one person need to do that. Maybe one person, or even less than one person. But in a classroom, you spend 99% of the time on those kind of calculations. What's good for that? The reason you come to this class is I'm telling you something surprise you and very practical. If you don't even know how the machine will run, then forget about the detailed calculation. What's a good detailed calculation to you? If you don't know, okay, when the breaker open and then when the breaker close it and then it trip again. If you are not ready for that, then why people hire you to do the protection? You don't even understand why is it. I'm saying, in case you don't understand, I will not say you don't understand. I know you understand. But just in case you don't understand, then what's good for that? Because I found a lot of academic discussion is on the detail. It's go into the equivalent circuit and do all kind of calculation into the decimal of 6 places. What's good for that? Who pay for it in the real life? I don't need you to find the parameter of the rod rotor, low rotor, and all this kind of things, and I know how to do the calculation. No one asks you to do. People ask you why you run. If the motor's stuck, what should I do? What kind of protection I have to put it in? Okay. So why I concerned, because a few months, 2-3 months down the road, you have to make a living. You have to make a living, no matter what grade you get. It doesn't matter. As long as you pass, qualify to be a professional engineer. Even your GPA is 2.01. That's good enough. If you cannot qualify as a professional engineer, that is a totally different story. But you don't need to be 4.3. No. It's good to have. Don't get me wrong. It's good to have a good GPA, but it's not the focus. The focus is, can I do the design? Can I provide my professional service? And people can take my service and with value. If I cannot even answer this question, you say, oh, inrush current, why I don't even understand there's an inrush current. I know that in the classroom is talking about it, but I don't get the feeling. Believe me, you only get the feeling you can do the good design. It's not someone mentioned. It's not the textbook mentioned. You need to know. You need to have the feeling. Okay, I fully understand what is it. Then you can do the design. Otherwise, it's very dangerous because you miss something. The equipment will blow in front of your eyes once you close the breaker. It will blow in front of your eyes. It may not only damage the equipment, damage the facility, interrupt the production. It may also get someone harmed. That is more important than any grade. Okay, my GPA is 2.01. I survive. Do you believe it? Okay. No. Good GPA is always good. Don't get me wrong. I'm just saying we need to know the basic. You get to know the feeling of what is going on. So is anyone can tell me why the transformer inrush current? You have to learn all the electromagnetics, you have to learn machine, you have to learn transformer, you have to learn, and all this you have to learn. If I ask something you haven't learned, then I'm not right. I ask something you have to learn, not only once. You have to learn maybe more than once. If a induction motor and a transformer connect into the system, which the inrush current compare with the rated condition, which one is higher and why? If we cannot answer this question, then what's good for that? Because people will not have the confidence you can do a design. You don't know the very, very basic things. So I leave this, maybe I get you, caught you in a surprise. I give you this as a homework thinking. Okay, just thinking about it. And then we talk about in the next lecture. So you say, no, if you ask something to me, I may need some time to think. Because I don't know the classroom tell you how much you are supposed to perform in the real world. Okay, in this course I will tell you. Okay, if you need some more time to think, do not hesitate to tell your boss, I need more time. Don't rush for the solution. This is not an exam. The exam can be say, okay, I fail, but in the design, I fail, I may kill people. So you just tell people, wait a minute, I'm not in the right mind now, or you caught me and I'm prepared. Okay, I need time to think about it. Okay, I need time to think about it. It's perfectly fine. You don't need to rush for the solution. Okay, this is very important to remember. Okay, you will not lose a job because you have a reasonable request for thinking. If a good boss, or well, most of the bosses are very experienced, may not be good in the sense of the feeling. Okay, but they are, because they can be a boss. That means they also go through all the process. They also have all this. So if you come up with say, I need time to think about it, they will not look down on you. Actually, they will be appreciated. If the junior engineer working under me to say, wait a minute, I'm confused, I need time to sort it out, I always give time. Because don't rush, because the consequence is so huge. So this is something I want you to learn, not only from this course material. Okay, particularly this kind of contradicting things and all these kind of things. If you need time, you tell you need time. So again, in the final exam, I will not ask you anything I don't mention in the class. I will not, because in the exam is not you. Sometimes you just caught you by surprise. But if I have mentioned not only once in the classroom, in the lecture, then I ask you and you don't know, then I make a course, I don't give any mark, I think it's reasonable. In case in the exam, if I ask a question, I never mention it, don't be excited. Just do the question and send me an email. This question, this part you never mention in the class. Then whoever can answer correctly, it will become a bonus question. Whoever cannot answer it, no mark deduction. And actually, I will apologize. Sorry, I don't know why I missed that. Okay, it's not your fault. If you can answer, great, it becomes a bonus on top of the 100%. So let's make this agreement. Okay. So anything I ask in the final exam, of course, I say 2.0 is good enough. No. We want better marks. I want everyone is most of my classes is average is A minus. Okay. So I want people to earn that, and also to make sure you don't worry about something I ask you and caught you in the middle. I always mention in the class. Okay. I will always mention in the lecture to make sure you are well prepared. Okay. For example, I put out a short question is how many percentage of the inrush current for a typical transformer, and how you design your protection. Then if you don't come to the class, the textbook may not mention. But if I ask this kind of question, is it reasonable ask? Of course it's reasonable, because the inrush current is always there. Okay, if you cannot decide, and then when you close the breaker, it trip again. When you close it, it trip again. And you don't want to close this the third time, because it may damage things. But you say, no, the textbook doesn't mention. The textbook mentioned in a sense, may not be from one textbook, may not be from one course, it mentioned. Okay. So I leave this just for fun. Okay. And then you remind me in the next lecture to give you the answer, or you tell me the answer. It's better you tell me the answer, not I give you the answer. That's not right. I tell you the answer is not right. Is you tell me the answer. It's better. Okay, because you have I know it. Okay. Now the more better drawing of the inverse curve is this set of curve in the relay. Okay, so a bunch of inverse curve. Now we have the selection in. Okay, in the protection is already almost 100 years. Okay, so at that time it's using electromechanical. You change the law. Now we use digital, but the digital is just to repeat the electromechanical relay. The characteristic is the same. We program it in the inverse curve is the same as this. So what is 1, 2, 3, 4 to 11 is the dial setting. That means is you pick up which curve for your design. You pick up curve number 2. You pick up curve number 2 or curve number 10 in your design. We will go through it. Okay, this is the electromechanical relay. There's a lock. You can turn it to 1, 2, 3, and so on. You can turn it. So that is a dial setting. Okay. So don't need to worry about how you do it. I will tell you. I will tell you the solution. I will tell you the solution. One solution. Okay. I will tell you one solution, and you do your design. Okay. Protection of a network. That means network means it's more than one source. In a network, there may be different sources, and the power in a line will be bidirectional. Okay, the line can be, the power can be flow from the left to the right, from the right to the left. Bidirectional, we are talking about one line. and the whole network can be anywhere, flow anywhere, but we are looking at one piece at a time. And the network, why we need to have more sources? Because we want to increase the reliability. If one source is gone, the other source will pick it up. Okay, so we don't want to if there's only one source come into Ryerson, when that source is gone, the whole Ryerson will back out. No, we want to put two or three more sources into Ryerson, and then switch on to the source with no problem. And particularly in a transmission line, if you have a very heavy power, heavy load, and usually will have more than one source. And sometimes it's also in the distribution, particularly in the urban area. Okay, in the urban area, is you don't want to back off the whole downtown. Okay, there's too much economical loss. Okay, we move it when a particular element is, we open up the breaker. And if you have somehow to come here, you want to open up the breaker in both sides. Okay, we'll come to that in detail. The common protection, because in a different direction, we have a directional relay. Again, we will do the design for that. And we have an impedance relay. We also do the design for that. And the differential protection. Okay. In the directional relay, then we use the voltage and current because most of the load is lagging. The current is lagging. So you have a voltage here, and the current is lagging because most of the load are inductance and resistance. Okay, so the current is lagging. And if you measure in this way, and you define the CT direction, in this way, then you find this one, then you know the power is flowing from left to right in this drawing. Now, if the current is leading, this is current, still using the voltage as a reference. Then you know the current is going backwards. So from the current and the voltage, because we only use voltage and current. Okay. From the voltage and current, you will know the direction. And then you decide whether the power is flowing from left to right or from right to left, and how to protect it. Sometimes we want to identify where is the fault. For example, from boost power, bring a line to, of course, through a different substation, transformer station and all this, but we just make it simple, particularly in before it comes into the load. Okay, then there's a long transmission line. Okay, of course we hang on to the towers, and then there's a high wind to break one line and short the circuit. We want to identify where is the break, so we can send the crews, the worker to fix it. So we want to from the impedance. If from the impedance, we know the cable size, we can calculate the impedance. That's what you have done that in your last course. And we are going to use it. Okay. And then you can identify where is the fault, and you can send the people, because it may be a long drive, maybe an hour drive. Okay, you can send the worker there in a very close to that location. So you are rely on the impedance relay, so you can identify where is the fault more better than just searching, because the line sometimes is across some valley, some hill, and all this is may not be easy to accessible. Okay, so and you want to return the surface as quickly as possible. Okay, so we'll do this, and again, how to do that Ohm's law. Okay, it's an Ohm's law. Okay, so it's proportional Ohm's law. Power is very simple. It's very simple. So you pick a good career. Okay, because after you graduate, you have other enjoyment in your life. You don't need to spend all your effort just to make a living. So power, you pick a good one. But remember, the consequence is huge. The consequence, if you don't do a good job, the consequence is huge. You not only damage things, you may kill people. Okay, so we have to be very careful. But things are very simple. Ohm's law, Faraday's law, Ampere's law, that's all. So in the impedance relay, we identify zone 1 is 80%. You don't need to remember this. I will give you an example and all this to make sure you are well prepared. Okay, well prepared. I just mentioned it since it's already there. I mentioned it. For zone 1 is 80% of the line. How 80% and all this, and if a certain situation, it may be do it differently. But anyway, that is most of the textbook do. And when you join the hydro or to join the company, you have to ask the experienced people what are their settings. 80% is just a textbook reasonable suggestion. Okay, don't try to argue with people about if they use 75% because of particular reason. You have to use it if the reason is good. So or they want to have 90%. 80% is not case in the stone. It's just a suggestion. It's just a reasonable percentage to use. And then zone 2 is more than that line. It's cover the other zone, and why it cover the other zone we'll discuss. It's 120% more than the line itself. It cover to the other zone. Why we do that? We'll talk about it. And then zone 3 will be 2 line 1 and line 2 together. Okay. Here mentioning it because of the back out in 2003, and this try to reduce the zone 3 because they doesn't want the worst condition is cascade on and back out the whole area. But you still learn zone 3 is the 2 line add together. Okay. Okay. And you learn the symmetrical component. Okay. It's usually we would start with a three-phase fault, but it say it can give a very limited protection for 9 to 9 fault, not 9 to 9 to ground, 9 to 9 just the when the two cable, when they're in a high wind, the two cables swing, and for usually this will not happen in a new design, because even if swing, it will not touch each other. Okay, it will not touch each other, but maybe in some old area, it saves the number of tower. It may be long enough, it's set enough, and then when it swing, you may touch, or the insulation breakdown, it will short circuit 9 to 9. Okay, so you calculate the 9 to 9 fault and work out fault current or three-phase fault, which one is larger and how, or which one is smaller, and how to detect it. So we will cover all this. Differential relay. Differential relay is, for example, in the transformer. Okay, in the, say this is a transformer, or this is a bus or transformer. All the current go into one location is sum up equal to 0. Again, it's very simple. It's circuit theory. Okay, so we have to detect that. But if this is a transformer instead of a bus, you are taking into account of the turns ratio. Okay, because primary and secondary are different turns ratio, and the current you have to taking care of it. Okay, it's nothing. You learn everything. You learn everything in this course. We just use it. We have to use it carefully. That's all. Okay. There's other types of relay, and we'll come into that. For example, under frequency relay and over frequency in a generator, under voltage in the low. Tell me for under frequency. Oh, sorry. Particularly in this situation, because I'm looking at the iPad, I didn't look at the screen. I didn't know it's gone. If that is the case, please yell. No, it's not there. Okay, so we are equal. Okay, or even I have to serve you. So if something is, for example, the screen just off, the iPad does not send it to the computer, and you don't see anything. So please make noise. Okay, please make noise. I didn't, because my eyes is not looking at the screen. I'm looking at my iPad is still there. So if I don't know how long you have been off. I hope it's not long. Okay, so in this kind of case, please do not hesitate. Do not hesitate to say, no, I don't see the screen. Okay. Is everybody is still awake?
Yeah. The screen's still there. You're
good. Because I don't know. I cannot see your face. Okay. Yeah. Okay. Okay. My question is for the under frequency. Why we have to protect the under frequency? Why we have to protect under frequency? You learn frequency for sure. Okay. Okay. Why under frequency we have the concern? Okay. Why has the concern for the low? Okay. Again, I put that as a question. So we can answer all this. If someone remember what I asked you to think about it, and next lecture remind me to remind me your answer, or you ask me to give you the solution or give you my idea. Okay, so I don't want to catch you in the middle. Okay. Okay. A lot of time we want to recall it if there's a failure. We want to see the sequence of event. We want to recall the sequence of event because we have to. There's two. One is engineering. One is legal. One is legal. One is non-legal. Okay. Okay. For engineer, we want to know what's happening, whether the protection is sufficient or not. From legal point of view, for the insurance, they will know whether you do the property design or not. If you don't do the proper design, proper maintenance, they will not pay you. They will not pay the damage. Particular, I just have one consultant. Is still going on. Okay, one of the transformer blew up, and the production stop. Yeah, so replace the transformer. You lost lots of revenue because of the everyday protection. Everyday production is off. I'm hired to have an audit to know what's going on. Okay, whose responsibility? If it's natural, if it's equipment naturally, if it's equipment naturally deteriorate, aging, and cause the transformer blow, that is true. I'm doing it now. Okay. Okay, that's why you come into this class. I will tell you all the things you may not usually listen in the other course. Okay, it's a different perspective. I do lots of consulting work. Okay, I do lots of consulting work. Wherever it comes to certain point, I recall what my experience. I will tell you. Okay, so I'm asking to find out whose fault. Then I have to look at the sequence of event and then decide. Particularly something is already burned. It's very difficult to trace. Forensic investigation is challenging. I'm telling you, and you have to be fair for both sides. Okay. So whether it's a design fault, you say that's. I just give you an example. Someone saying, "Yeah, I designed protection. It works for 20 years." Oh, you're just lucky, because what you decide to protect, that fault condition did not appear, did not occur. So you are lucky, not because your design works. So because it involves a huge amount of money, huge amount of money. I cannot tell you how much money involved because of the confidential of the client. Huge. Then everyone is pointing the finger to each other. Just say, no, this is natural. The other say, no, your maintenance is not ethical. How can I insure you? You don't do the regular maintenance. Of course, you will fail if you don't do the regular maintenance. So you need to know the protection well enough beyond. You need to know the protection beyond the design, beyond the textbook. And because a lot of things are no longer available for you to observe because it's already burned out. Okay, so hopefully by the end of this course, I finish that project. I tell you what I found out. Okay, because it's a huge camp. Okay. Okay, now it's more fancy using GPS for the location of the fault and all this, yeah, and the fault calculation using the sequence network. Okay, let's take a 10 minutes break. and then we come to the project. I tell you how to do the project. Okay, let's take a 10 minutes break. So I will not ask you to do anything offhand.
Professor, will you be posting the slides?
This is just from the textbook. Well, yeah, I don't mind. I can post it. I can post it. It's just a summary. No. If you want, I can post it. Okay, I can post it. But I don't see any value. Okay, let's take a 10 minutes break, and then we do the project. I do the project with you, and the good things is not only one solution. So you can remember to get a good mark or good grade is not the objective. The objective is to learn the things. Even I give you a solution in your project report, you do something else. Don't just present that solution, because this course is really important in power. Most of them are protection. Others is you learn all others is because of this. Okay, so you don't want to give up the chance to learn and exercise and all this. Don't worry about the marks. The marks is not a concern at all. Don't worry about the marks. Marks is nothing. Okay, so marks is nothing. The knowledge is everything. Okay, so let's take a 10 minutes break. Okay, thank you for still being haven't left. Okay, I appreciate that. I still have a good class. For those who are missing the lecture, if you have a chance for a good vision or whatever, if you know the person, just tell them, because in the exam, I may ask some question. Even you don't come to the class, you are supposed to know, but it may be difficult in one sense. Okay, so it's not you haven't learned it, or you cannot learn it by yourself, self-study and all this. Yeah, you can learn it, or you have already learned it from the other course. But during the exam, it may be challenging to remember all this and put them together to give a correct answer. Okay. Now for project 1, I'm going to tell you my design. So you don't want to repeat my design into your project. The design itself will bury the signature of the designer. Okay. So my design is the way I think is after judge this and that and maybe the equipment available in that case and all this, I make that kind of assumption and come up with a design. That is is not 1 + 1 = 2. Okay, that kind of question, because a lot of flexibility. So you don't want to tell your sponsor. Your sponsor may be yourself, who pay the money, or your parent. You don't want to tell them, I learned how Richard Chong is sign the paper. I learned Richard Chong's signature. Well, your sponsor, including yourself, will be very, very mad. Okay, your own signature is important. How I sign is not important. It just, oh yeah, that's how the way he signed the paper. Just one way. So I truly believe you will come up with your beautiful signature, not my signature. Okay, so I'm not worried about, I tell you my design. Okay, and you come up with your design is more important than my design. Okay, and I strongly believe your design is better. Okay, so under that situation, I'm telling you my design. Okay, but don't repeat that in your design. Don't repeat it. Okay, do your own design. Okay, do your own design. Okay, just under this condition, I will test this out. If this doesn't work, I will try something else. Okay, so I strongly believe you are not happy with my design. You are happy with your own design, your own signature. You have a beautiful signature, better than mine. Okay. Okay, sorry. Okay. Okay, let's talk about the first, design and verify the protection of a transmission line shown in figure 1. So shown in figure 1. Okay. And this is the transmission line and fed by 2 generators. And it has several major loads. And this load itself will expand. This load itself will expand. This load itself will expand. Okay. Use the data in the following page. So what data in the following page? Okay. So each group will have a different data. It just changed a little bit. How come it doesn't show? Okay, yeah. Oh, okay. It just a tiny delay. Okay, maybe. Okay, sorry. My internet is very slow. My internet is very slow, very bad. So, but anyway, is the project is already posted. Okay, so each design has its own set of value. Okay, its own set of value. I use one set of value. Okay, only change a little bit. Only, for example, in group 1, the impedance of generator 1 is 14.6, and group 2 is 14.7, and group 3 is 14.8. Just change a little bit, okay? And others too. So which group is assigned by your TA, okay? Okay. So the parameter is make it in general, such that each group will do their own design, and the transmission line is also with a variable impedance, such that each one will have their own design. Okay, because the bottom line is forget about the marks. Who care about the marks? Okay, if we do a reasonable work here, you cannot fail. You cannot fail, because you come to the class and do a reasonable work. Okay, so let's put the mark aside. Let's focus on the learning. That's why I put a different set of questions and put a different parameter, and just to remind us we have to do our own. Okay, because in some others is you just keep on copying. Is no, you don't want to reply to your sponsor. Your sponsor may be yourself. Say you don't learn anything. Okay, verify. You can I don't know how you do before. You can use the E-tab. Before you can use the E-tab in the school to do it, but now the school engineer Jason tell me you can download a working package, and I will tell your TA and see whether it works out. Okay. And because this COVID-19 is catch everybody in a surprise. So verify is, if not, you can do a hand calculation to verify. Say if you have a breaker and the relay for the breaker B12, and that is a setting, and you assume a fault in the middle of the line, 1/4 of the line, 3/4 of the line, and see whether your relay will operate. Okay, you can do a hand calculation. I prefer you do a E-tab calculation. Use a computer verify, but see how it works out. I ask your TA to explore it. Use the engineer from our department suggestion to get the E-tab working. Okay, so or some of you has a better idea in this environment. I'm not in that good situation to to that. I leave this to the TA. The worst to worst, you can do a hand calculation to convince yourself by assume a fault in some location and see whether the protection is operate the same way as you expected. Okay. So using the data of the network and to decide the setting of the relay for this breaker 1, breaker 1, 2, breaker 2, 1, breaker 2, 3, and so on, and provide all the design calculation in detail, okay, in detail to justify it, and verify, assume some fault occur in this location, and see whether the breaker operate correctly in the design you have. Okay, and this is the first part. The second part is SAM, is a radio system. Okay, I don't know why. My computer is so slow. It's incredibly slow. It's incredibly slow. Oh, sorry about that. It's incredibly slow. I didn't know. I didn't recognize. I didn't recognize. I didn't recognize it's so bad. Sorry about that. My internet has a problem. Sorry about that. My internet has a problem. Oh. Sorry, my internet has a problem. So let me try again. You can still hear me, right?
Yes.
Okay, sorry about that. It's out of my control. Okay. Okay. Thank you for your response. Thank you for your response. I appreciate it. I apologize. Okay. For the radio system, then this is compared to here. So we are talking about the low one. The low one is a radio system. Okay. The low one is a radio system. So I want to make an equivalent circuit. I put all this become an equivalent circuit. Okay, and this is equivalent to this. Make an equivalent circuit. Just put a circle called V1. V1 is the one I equivalent the whole circuit. Okay, after you do that, I will tell you everything. Don't worry about that. I will, because protection is so important in your power career. Others is you really depends on where you hire, where you get your job. But protection is everything. Protection is everywhere. Every aspect your protection. So this is you pick a very good course, okay, in your selection, because it's everything. You power electronic, you need protection. Everything you need protection. Okay, that and or motor driver, whatever you need a protection. Okay, so that's why I will tell you the solution, but you do your own. Of course, you have your own idea how to do the design and everything. So I strongly believe you are not happy with my design. You will be proud of your own design. So we put the equivalent circuit with a equivalent impedance and equivalent source to represent everything except for this load. This load is this load. It's a radial system. Okay. Radial system has it defined as one source. One source, it tap off a different load. So now to ask you to design the relay for the breaker 4, 5, and 6, and then verify if I have a fault here, whether it operates correctly, if this is stuck, whether this backup is working properly, you verify it. Okay. Okay. Now, first, in your last course, in your last 746, you try to put everything into per unit. Okay. Because of the convenience of calculation. In your per unit, you don't need to worry about the turns ratio of the transformer. Okay, because your turns ratio, after you define the base, the turns ratio is already taken care. So you do the calculation or analysis into one unit, or common unit. Okay, in a common unit. So it's easier to do the calculation. Now, protection is different. Protection, you have to do the setting of each one. So it's opposite. You want to go back to non-per unit because you have to go to set how many M, how many impedance, what are the ohm. So you have to go back to non-per unit. But a lot of equipment from the manufacturer is giving percentage per unit, percentage in the sense of per unit. Okay, per unit is a common base for everything based on the rating. Okay, so it's opposite. So this one is, if you look at for example, the subtransient reactance of the positive and negative and the neutral. Okay. Do you know why it's subtransient reactance?
It's going to be the highest. Well, it's going to give us the highest fault current.
Yes, because very good. I don't want you to identify yourself, but I really appreciate you give me a few answers. Okay, so I really appreciate. I really appreciate, because otherwise I'm talking in the air. Okay, when there's a fault, it will be going like this. The first, okay, so in general, we just make an ideal case. Ideal case is in general will be then come back to steady state. Now this can occur is continuously, but continuously we cannot do the design, or we cannot do the analysis. So we have to, because continuous is is you need to solve the differential equation, and all this is impossible to do. Okay, and also not necessary. If something is necessary, even it's very difficult to do, we still want to overcome it, but it's not necessary. So we cut into three areas. One area is in the first 2 cycles of the oscillation or after the fault. Then this is subtransient, and then transient, and then the steady state. So steady state, we do low fall and all this. We have already get used to the steady state. We most of our previous course work are steady state, low fall and all this. Transient is the stability. Okay, we'll also touch in this course. The stability is a transient state. And the subtransient state is protection, because we have to, in the field cycle, we have to protect it. If we don't protect it, because the current is high, huge, compared with the steady state, the current is huge, and the damage is square. Because what will be the damage? The damage is a heat. The heat generated will break the insulation and make it worse and worse. And the heat is RI square. So this is huge. The damage is square. The severity of the damage is square. So the first field cycle is very important. We have to protect it. But later on, if we don't protect in the first field cycle, then no protection at all. It will burn it out already. Okay. So that's why we use a subtransient reactance. Okay. In the transmission line, the subtransient and in the transmission line, the subtransient, the transient, and steady state are almost the same. Do you know why? You learn it. You learn it. Do you know why? Don't tell me in the last course of your undergrad study, you find out, no, I don't know this. You learn it in your previous course. Again, should I put it as a question so you can think about it? Why the generator? Why the generator has subtransient is different from the steady state, and the transmission line is very close, and the transformer is different. The transformer is different. Why? Very fun. To answer my question is why. Is all you need to know is what? Ohm's law, Ampere's law, Faraday's law, and Lorentz force. Just 4 of them will answer every question in the power. Every question. Okay. Don't tell me you don't know Ohm's law. Don't tell me you don't know Ampere's law. Don't tell me you don't know Faraday's law. You don't know Lorentz force. If you know that, you can answer any question in power. Did your professor tell you that? Okay. If you need a typical knowledge to answer that question, then you say your question to ask me is unfair, is not fair. No, you just need this 4 basic things: Ohm's law, Faraday's law, Ampere's law. At most is because of electromechanical, then Lorentz force. Then you can answer every question in power. Okay. If people ask you what you learn in power, oh, I just learned 4 laws or 4 rules. Okay, that's it. And then you can make a beautiful new career, beautiful life. Okay, so you may answer me other time. Okay. Anyway, particularly in a generator. Okay. Okay. Now let me start how I make the percentage and get back to no, don't get me wrong. You have already learned it, you have already done it for sure. Okay. I hope you understand. I repeat it, not because you don't know. It just I repeat it such that to make sure you will not do it incorrectly. Okay. But if you think I do that is too simple to you, and you tell me, okay, you tell me, then I stop. Okay, then I stop. In my career path, I never things are too simple. I don't mind things to repeat. That's why I tell my junior engineer, I say, I'm talking about something you know already. I'm not talking about you don't know. I just want to confirm what we know is will not have any mistake. Okay, so the same thing apply to you. You say, yeah, I have done that because this is too simple. It's okay. Let me go for it. But if you find really bothering you, it's too simple, then I jump. Okay. So I get a blank page so I can write. So for the XG1 and subtraction use 2 pi, and it say is equal to 15%. I do my own design. Okay, you will have a different percentage. Okay, in your design. Okay, and the rating of the generator is 900 MVA, and the transformer is 18. Transformer is delta Y connection. Delta Y ground is 18 kV to 230 kV. Okay. First, I want to make this into a real unit because I have to set my relay. So what should I do? So this 15% is based on the 900 MVA, 18 kV. Then what is the base impedance? The base impedance will be V squared over S. So it's now which V you use? S, of course, you know, is you use the 900 MVA. Which V you use? 18 or 230 kV? Which one you use? Anyone can. I want some interaction. I'm not looking for accuracy. I'm not even looking. I just need someone to. Why you participate in the discussion is just to put yourself into the course.
Use the 18 kV side.
Okay. Any objection? It's only two choices, eh?
Oh, it's a 50% chance.
You know, I tell you the story. I go to casino. I always lost. Okay, I always very consistent. I buy big, it goes small. Then I test myself. I say, okay, now I originally think it's big. I buy small. I still lose. I'm very difficult. You find someone who are yelling and who are very upsetting in casino is me. Now, because of this experience, I never guess. I can guess in the casino, but in engineering, I never guess. Because I know I'm always pick the wrong side. Consistently, no matter how I change my mind, I still pick the wrong one. Okay, so in engineering, I don't guess. I will look at the problem, what I'm doing, before I pick it up. Even as you say, is 50%. Okay, so you present your idea, but if you say I just pick it up because I like 18, I don't like 230, then you are in my group of casino group.
No. But
if
I
you
was
have a
saying if
reason,
the generator is connected to the primary side, so that's why I would choose 18.
very good.
There we go.
Good.
Okay.
Very good. You have a vision, but your vision is it fit the objective of your work? I like that visioning. You pick 18 because the generator is on the 18 side, 18 kV side. Okay, I like that. No one can say no. But for doing the design of the setting for breaker 1, 2, and all this, and I pick a good choice. Now the breaker is on which side? On the 230 side. Okay, not on the 18 side. If you pick the 18 kV side, you have to convert it later.
Oh.
I hope you will come to my next lecture.
I will not miss a lecture, I promise you.
Okay. Let's have fun, because you learn everything in the other course. If I do the same thing as the other course, then that's no fun. Okay, so you put 230 because you don't want to do it again. You want to refer all the things into one setting to serve the purpose to find the setting of the breaker. So that's why even you are very logically, and no one can dispute it 18 kV because of all the good work visioning. Okay, but after you do that base, and later on you have to change the base again. Okay, are you okay now?
Yeah, I got it.
Okay, good. Okay, don't get me wrong. We just have fun. Okay, okay.
No, I get it. Sometimes it's just a little early in the morning before noon.
No, I want to present in this way is because this will stay in your mind longer. If I present it in a very formal way, okay, put it this multiplied by this, how long it can stay in your mind? No. If you say, I remember the lecture. Okay, when I do the calculation, I have to look at my objective. Okay, so it's not I try to say you're wrong, I'm right. No, never. Okay, it just put in a fun way, in a layman terms, we can remember much longer. Okay, so just remember the joke. Yeah, I put in the right voltage, and it turns out to be the other side. Oh, because I didn't look at one step further. What
Yeah,
I'm-
because of my gambling addiction, now I know which side the breakers are.
Good. Let's see in the casino and see whether you are right or wrong. No, don't go there. Don't go there. Don't go there. I lose my shirt. Okay, so you put the base, and the k square is the m, so the unit cancel, divided by 900, and multiplied by 15%. Okay, and it will be equal to, for my case, is 8.817 ohm. Okay, so you do the same thing for others. Okay, now change the base, and it should not be a problem for you now. Okay, again, in your group 1 and group 2 and all this group will not have the 15%, so you will not just, again, you don't want to copy. This is my signature. Okay, you have your own beautiful signature. Okay, so, but I want to tell you how I design it, and then you do a better design than mine. Okay, promise. Okay, now today is fine. Maybe if the last 5 minutes you prepare your mind for the other course. So I hope I can see you, or I can hear from you, or you attend in the next lecture. Okay, so if I can stay if you have a question, and we will not discuss any technical or whatever. Even if we discuss, I will repeat in the next lecture. So you are free to leave. If there are any technical, any significance, if someone stay behind and discuss some technical things, I will repeat it anyway. Okay, so you are free to leave.
Hi, sir.
Yes.
Would you be able to post the notes as reference?
No. That's my signature.
Oh, no, as in like just the lecture notes from earlier on, from the today's.
No. The looks will be the lecture looks will be posted, but this kind of design discussion I'm not going to post.
Yeah, that's fine. Thank you.
Yeah. Thank you. I will post that. Yeah, I will post the previous one. Yeah. Okay. Any other question? Any from anyone? Because I want people to come to the lecture, because it's not only one thing. It's not just calculation. Calculation is only a very minor things, so minor in your career, so minor.
Yeah, it's the practicality of it all, right?
Pardon me?
You got to be like very practical in your design.
Yeah. Because doesn't matter how I agree or I disagree with others. Okay, I think this way, because my experience 35 years a consultant in a very high price. Then I believe
Right.
I believe my things works. And it works. You don't hear any news problem in boost power or Pickering or Darlington. You don't hear. Okay, so my design must work.
I mean, for 35 years, yeah, it must work.
Yeah. Okay. Otherwise, they kick me out, right? They kick me out already.
Right. Exactly. Okay. Thanks. Have a good day. Eh?
Okay. Thank you.
Yeah.
I hope I can see you. Yeah.
Oh, for sure. Bye-bye.
Okay. Thank you. Bye-bye.